What does it actually mean for a particle to be in superposition? An often used example of superposition is a spin 1/2 particle. Maybe this is something you've seen before. Capital psi is the state vector or wave function of a spin 1/2 particle that's in a superposition of spin up and spin down. While this system is a good example of superposition, it can be a little abstract. It's hard to put your finger on exactly what spin up or spin down is. Instead, we are going to simulate a system that's a little easier to visualize and understand. We're going to look at a particle trapped in 2 neighboring wells. First, we need to select the potential. We're going to start with an infinite square well of width L. Now, to create the double well, we're going to add another barrier in the middle of the potential. This one will be reasonably tall, but unlike the other walls, it will be finite. Let's call the width of this barrier A. The height of this barrier will be V0. So now, we have 3 total barriers, one on the far left and the far right. These are the infinite barriers. Nothing's getting through these. And we've divided the space in 2 with the middle barrier, which is finite. This creates 2 separate wells. But because the barrier in the middle is finite, there is some chance, however small, that the particle can tunnel from one well into the other. Just like in the last video, we are going to represent the wave function as some number of points along the x-axis. In this demonstration, we're going to measure 2 different properties of our particle. In particular, we want to measure the probability that the particle is in the lowest energy state, called the ground state, or if the particle is in the first excited state. So now, this will be our energy basis, and if we want to know the probabilities of measuring a particle with a certain energy, we just square the coefficients of that particular basis as usual. The other property that we want to measure is the probability that we find a particle in the left well or the right well. Looking at the 2 energy basis functions, we can combine them to create the left basis function that we need. And the right basis formula looks like this. So now these functions will be our left and right basis. And if we want to know the probabilities of finding a particle on the left or on the right, we just square the coefficients of these basis functions. These probabilities will be what we plot in our bar charts. One more thing that we want to account for is time dependence. The wave function might move around in the potential. The energy basis has a special property that we will be exploiting. It turns out that the time dependence for an energy basis function boils down to just an additional phase factor. And this is exact, so we don't need to do any special numerical time stepping. And therefore, our state in this basis is this. And because the square of the phase factor is 1, the probability of measuring either energy is unaffected by time. The left-right basis is slightly more complicated, but it's not too bad. This is what our state vector looked like. And remember, this is the definition of the left and right basis functions in terms of the energy basis. So let's add the time dependence into these basis functions, and here's what we get. Okay, with all that in hand, let's look at an example state vector expressed in the left-right basis. Here we have a particle completely in the left well, so naturally the probability of measuring the particle there is 1. Now let's look at a superposition. If we measure in this basis, we expect to see the particle on the left half the time and on the right half the time. So far, this seems like a simple kind of uncertainty, but here's where things get interesting. Let's look at the same state, but expressed in a different basis. Let's use the energy basis from before. This means if we measure the particle's energy, we will get a definite answer, the ground state energy. In this new basis, there's no uncertainty at all. So what changed? Not the state, only the measurement basis. And this is the key idea. Superposition is not being in multiple states at the same time. It's about how the state relates to the measurement that you choose. Now, let's let the system evolve in time. The system will start with the particle completely localized in the left well. We're going to show what the wave function is doing here on the top, and the probability charts for each basis on the bottom. On the bottom right, we have the probability to measure a particle in the left or the right well. And on the bottom left, we're going to have the probability to measure either the ground state energy or the excited state energy. Each of these charts will change in time as the system is simulated. So we can see that the probabilities behave differently depending on the basis. Notice, when measuring the energy, the probability is constant. It's always 50-50. This is because, as we said before, the time dependence of the energy basis states is just a phase factor, and that phase factor doesn't change the magnitude of the coefficients, so the probabilities are constant. On the other hand, the left-right probabilities absolutely change. Sometimes there's a 100% chance to find the particle on the left, sometimes there's a 100% chance to find the particle on the right, and sometimes there's a mix. So, when we say a particle is in superposition, we don't mean it's literally in two states at once. We mean there exists a basis where the outcome is uncertain. And there's another basis where it's perfectly definite. Superposition is not about where the particle is. It's about how we choose to look at it. And that choice changes everything.